Example 1, part A, solve the differential equation. The derivative of y with respect to x is equal to x squared over x over y squared. Part B, find the solution of this equation that satisfies the initial condition y of 0 equals 2. See sidebar. Figure 1 shows graphs of several members of the family of solutions of the differential equation. In example 1, the solution of the initial value problem in part B is shown in red. Solution, part A. We write the equation in terms of differentials and integrate both sides. Y squared dy equals x squared dx. The integral of y squared dy equals the integral of x squared dx. 1/3 y to the third power equals 1/3 x to the third power plus big C, where big C is an arbitrary constant. We could have used a constant big C sub 1 on the left side and another constant big C sub 2 on the right side, but then we would combine these constants by writing big C equals C sub 2 minus C sub 1. Solving for y, we get y equals the cube root of x to the third power plus 3 big C. We could leave the solution like this, or we could write it in the form y equals the cube root of x cubed plus big K, where big K equals 3 big C. Since big C is an arbitrary constant, so is big K. Part B, if we put x equals 0 in the general solution in part A, we would get y of 0 equals the cube root of big K. To satisfy the initial condition y of 0 equals 2, we must have the cubed root of big K equals 2, and so K equals 8. Thus the solution of the initial value problem is y equals the cube root of x cubed plus 8. All right. Example 2. Solve the differential equation dy over dx, or derivative of y with respect to x, equals 6x squared over 2y plus cosine y. Sidebar. Some computer software can plot curves defined by implicit equations. Figure 2 shows the graphs of several members of the family of solutions of the differential equation in example 2. As we look at the curves from left to right, the values of big C are 3, 2, 1, 0, -1, -2, and -3. Figure 2. Back to the text solution. Writing the equation in a differential form and integrating both sides, we have open 2y plus cosine y close dy equals 6x squared dx. The integral of open 2y plus cosine y close dy equals the integral of 6x squared dx. Then you get equation 3. Y squared plus sine y equals 2x cubed plus c, where big C is a constant. Equation 3 gives the general solution implicitly. In this case, it's impossible to solve the equation to express y explicitly as a function of x. Example 3. Solve the equation y prime equals x squared times y. Solution. First, we rewrite the equation using Leibniz notation. Dy over dx equals x squared times y. If y does not equal to 0, we can rewrite it in differential notation and integrate. Derivative of y, dy over y equals x squared dx. Y does not equal to 0. The integral of dy over y equals the integral of x squared dx. The natural log of the absolute value of y equals x cubed over 3 plus big C. Sidebar. If a solution y is a function that satisfies y of x not equal to 0, for some x it follows from a uniqueness theorem for solutions of differential equations that y of x does not equal to 0 for all x. Returning to the text. This equation defines y implicitly as a function of x, but in this case we can solve it explicitly for y as follows. The absolute value of y equals e to the power of the natural log of the absolute value of y equals e to the power x cubed over 3 plus c, which equals e to the power big C times e to the power x cubed over 3. So y equals plus or minus e to the power big C times e to the power x cubed over 3. We can easily verify that the function y equals 0 is also a solution of the given differential equation. So we can write the general solution in the form y equals big A times e to the power x cubed over 3, where big A is an arbitrary constant open. Big A equals e to the power big C, or A equals negative e to the power big C, or big A equals 0. Sidebar. Figure 3 shows a direction field for the differential equation in example 3. Compare it with figure 4, in which we use the equation y equals big A times e to the power x cubed over 3 to graph solutions for several values of big A. If you use the differential, if we use the direction field to sketch solution curves with y-intercepts 5, 2, 1, -1, and -2, they will resemble the curves in figure 4. See figures 3 and figure 4.